So we've been looking at solubility and how we can start to calculate our different types of problems. Here we've got a new one where we're looking to see whether or not any precipitation forms when we mix these two things together. Well, wait a minute, what are we mixing together here? We've got two aqueous salts, sodium ions, sodium compounds, always soluble, nitrate ions, compounds, always soluble. When these get mixed together, we're trying to make a precipitate, so something better come out. Well, it's not going to be sodium nitrate. Our only other option would be the calcium fluoride. And so the question becomes, if we mix this amount of our calcium nitrate with this amount of our sodium fluoride, would we get enough calcium fluoride produced to form a precipitate? Well, we know that a precipitate would form if we have overcome or oversaturated beyond that KSP value. Our KSP is the maximum amount we can put into solution before we've reached saturation, maximum solubility. And so really we're looking at a snapshot. We're looking at one moment in time and how that compares to what it would be at equilibrium. Well, that's really describing Q, our reaction quotient that we saw in chapter 18. And so if our Q equals K, if where we are currently matches the solubility product constant, we're saturated. We've reached all the saturation we get. If Q is less than K, we're undersaturated. We're not yet saturated in our solution. If Q is greater than our KSP, we have oversaturated the solution, and we would expect a precipitate to come out to return us back to KSP. And so we can start to do a little work. Well, we're trying to make calcium fluoride. Calcium fluoride. Well, we're going to need to know how many calcium ions are floating around in there and how many fluoride ions are floating around in there. Well, we can figure that out by using our molarities in liters. We know that molarity equals moles over liters, so if we multiply these two values together, we can get how many moles of calcium nitrate are in solution. Well, the good news is that for every calcium nitrate that dissolves, we get one calcium 2+ ion, so it's actually a direct relationship. It's a one-to-one relationship. So our moles of this is also the moles of our calcium 2+. We can do the same for our sodium fluoride to find our fluoride concentration. So by taking our moles, our molarity, which is just moles per liter, so here's our molarity times the liters, we can get the moles. Molarity times liters, we get our moles. Here's our reaction. Our calcium fluoride is going to form if we've got our calcium and our two fluoride ions. Now, the reason why this question gets a little tricky is we're actually summing these two volumes. We're pouring both our 0.100 liters and our 0.20 liters into the same solution. And so while we know our moles, now we can find our new molarities for these two, our calcium and our fluoride ions, using our new total volume, our 0.300 liters. So we change it back both into molarity, and now we know in our final solution the concentrations of our ions in question. Well, good news, our Q expression is the exact same as our KSP expression. It is our products over reactants. Don't have to worry about our reactants because this is a solid, raised to their coefficient or stoichiometric values. That's where our 2 came from that balanced chemical equation. So we take our values, we plug them on in there, and we solve for our Q, and we get 1.6 times 10 to the negative fourth. Yay, we got a number. The question becomes, how does this Q compare to our KSP? Keep in mind your sign connotation here. Times 10 to the negative fourth is a much larger number than times 10 to the negative 11th, which means we have oversaturated the solution, and we would in fact see a precipitation. Calcium fluoride would start to come out of solution as these two substances start to mix. Cool. Given this example, take a second, pause the video, and try to see if you can figure out this next question. The nice piece about this problem is that we don't have to worry about the volumes here. We're saying we're adding just enough molarity to make it happen, so we can actually jump directly to our reaction. Magnesium hydroxide is our precipitate that we'd expect to form. And our Q expression would look something like this, our magnesium 2+ times our hydroxide squared. Here we get to plug our values in straight away because we're not worrying about a volume change. We can plug and solve directly. We find our Q to be times 10 to the negative 14th compared to our KSP, which is times 10 to the negative 12th. In this case, our Q is less than K, and as a result, we would not expect any precipitation. Regardless of the fact that we've added these two things together, we would not see any come out of our solution. Here's another one for you. Give this a shot. Here, we know we're trying to form a precipitate. So we're trying to get to the point where we are just past our KSP value. Well, we know the KSP, and we know the concentration of those magnesium 2+ ions in solution. What we don't know is how much hydroxide we have to add, and so that's what we're trying to figure out. That's our X. Here we're going to solve directly for the hydroxide concentration, so we don't have to double it here. We're just going to square it based upon our our KSP or Q expression. Little manipulation here. So we would divide over our 1.5 times 10 to the -6. That goes below our KSP from our value here. And then we would square root it to get rid of our squared value here. And so by solving in this method, we can solve directly for, okay, what hydroxide concentration? Now, technically, well, this number here is still at KSP. This would be saturation. So in order to precipitate, it would be the moment we add one particle more than this concentration. And so this is kind of our stop point. Anything beyond that, we would start to see a precipitate form. Cool. Now we can start to think of our equilibrium expressions based upon these KSP and QSP values, our reaction quotient and our equilibrium quotient. We can start to then consider our Le Chatelier effects, how we can start to disrupt this equilibrium system. So if we had a balanced equation, we could start to see how our acid would react. Lead to bromide. So if we had our lead to bromide in solution, it's going to try to dissociate. We're adding a positive ion here. It's going to try to react with our negative species, our bromide ion. Well, that would form hydrobromic acid. Well, hydrobromic acid, that's considered strong. So it would in fact immediately dissociate back into solution. And so the addition of hydronium here would not cause any change in the solubility of our lead to bromide ion. No effect. If we had something like copper 2 hydroxide, our copper 2 hydroxide would try to dissociate to a small amount into our copper 2+ ions and 2 hydroxides. And hopefully you can see we've got now a strong acid reacting with a strong base. These are going to neutralize to form water, minimizing or reducing the amount of hydroxide ions in solution. As a result, we've disrupted the system. We've decreased the hydroxide. Well, Le Chatelier says if we stress a system, our system is going to move to undo that stress. And so if we have removed hydroxide, this is going to react to make more hydroxide. And so we would expect this to shift to the right. As a result, more of our solid will then dissociate into solution. We would say that it shifts right, and our solubility would increase. We would get more copper ions in the solution if we were to acidify the water. And oftentimes when we work with these complex metal ions, if it's a reaction or a species that reacts with water, by acidifying the water, we can actually increase the solubility by making sure we have more of those ions going into solution. All right, I promise, last K, at least for now, for this unit. Kf. We do have an additional kind of type of equilibrium constant. This is our Kf. It's known as the formation equilibrium. The good news is we've actually done a version of this before when we had our multi-step equations and we were trying to combine them together to see what our final equilibrium expression would be. Good news, the math is pretty straightforward. And so when we start to form these complex ions, when we've got our copper ion reacting with water to form this complex ion, we've talked about complex ions before we did our last qualitative analysis lab, we actually can find a Kf value, a equilibrium formation constant. And this is because of the number of species you've attached. This becomes incredibly soluble in terms of our species. Our original species becomes much more soluble. The extent of our dissociation, if we were to flip it, if we were to go in reverse, if we were to reverse this process, it's just the reciprocal. Our products over reactants, again, we wouldn't really worry about the water here because pure species. Products over reactants, well, it's just the inverse of our formation equilibrium constant, because we've reversed the reaction. Our products are now the reactants, reactants are now the products, and so it flips. And so you can actually solve, if you want to know the dissociation complex, it would just be the reciprocal of our formation value. This comes because we start to see these ligand pairs starting to join together as we increase the hydrogen bonding present within our species. We know that this will start to attract more strongly to our water, hydrogen bonding being fairly strong intermolecular force, we expect these substances to increase in solubility significantly. Turns out we can actually go about starting to find what these new solubilities would be. I know this looks like a lot. We're going to step through this so that you've got a solid example to look at. So here's the question. In pure water, the solubility of silver chloride is slightly soluble, we would say, 1.9 times 10 to the negative third grams per liter. What is the solubility then of silver chloride if we were to add it to a 0.010 molar ammonia solution? Well, all right, here's what we've got. We really have our silver chloride reacting with our ammonia to form our complex ion and our chloride species. Well, if we think about it just in terms of our dissociation, we've really got two parts. We have our silver chloride trying to dissociate, and then this silver ion is reacting with that ammonia to form that complex ion, that Kf, formation constant. All right, well, Ksp, that's a constant. There's a whole table in the back of the book available to you. Kf is specific to the complex that you're forming. That would be a little more specific. I would provide that for you. The question now becomes what is the solubility of this new species in solution? Well, we need to figure out how much of this is going to dissolve, and it's dependent upon two equilibria. How well this silver chloride dissolves, based upon its Ksp, and how well this complex forms, based upon its formation constant. The good news is to combine those. If you remember, when we combine our equilibriums, we just multiply those values together. And if you want, you could write out the Ksp expressions for both of these, and then write out the Ksp expression for your overall, and you would find that to get this overall expression, it's going to be these two expressions multiplied together, bearing in mind we don't include the solids. So if we want to find that overall equilibrium, the K net, we would multiply those two values together. Those were provided for us. Multiply those together, and we can get our new K net. Cool. That's great. Times 10 to the negative third. Ooh, that's to a magnitude that it might actually affect our initial concentrations here. So we've got kind of three concentrations that we are forming. We've got our silver ammonia complex, our chloride ion concentration, and our ammonia concentration. We know initially we've got 0.01 molar ammonium. We don't have any of that complex formation yet, and we don't have any of that chloride forming. Again, we're looking at kind of this, what's left after our solution has reacted. The reason we don't have to worry about the silver is because that silver actually cancels out as an intermediate from our two steps here. Plug in what we know, plug in the change. We don't know how much is going to change, so we plug in based upon our balanced equation. We know this is going to be using 2 ammonia for every one of these, We can then plug into our expression. We've found the K net from our multiplication here. We can then solve for x. This did come out to be a quadratic. I would never ask you to do that. I just am using this as an example to show you how these problems would be solved. Then we can figure out what that chloride concentration would be. Oh, okay, because x is our chloride concentration. Cool. But now the question is, what is the solubility in grams per liter? Grams per liter. All right, this is moles per liter, so we got to do a little work. Really, we got to multiply our moles by the molar mass. And, oh, we were already in liters, so really it's this value times our molar mass of silver chloride to get our grams of solubility, grams per every 1 liter. Cool. Feel free to go back, review this. There was a lot going on right there, but feel free to reference this as many times as possible. Really, again, the big piece here is to find your new K net. When we're forming these complex ions, it's going to be that formation times the Ksp. Those two combined are going to tell us how well our new species, how well that new complex ion is going to dissociate into solution. Cool. Another example for you here. Feel free to pause it, give it a shot. This one, again, is going to have a summation of the volume. So we're going to have to solve for moles, and then we're going to have to find our new volume of 75 liters. To find our new molarity. From there, we can assume that all of it has reacted. So we'd use 4 times the amount of ammonia. Sorry, let me go back to the balanced equation here. Based upon our complex, we're going from our 4 water molecules to 4 ammonia molecules. So our balanced equation would look something like this. We know we used this much of our ammonia based upon our balanced equation. We can then go in and start to plug in some of our values. We know our initial amounts here. We didn't have any of that complex formation yet. This was based upon our initial amounts of ammonia and our zinc hydrate ion, excuse me. We know that approximately all that's going to get used up. Ooh. We know that, sorry, let me fix my box here. And we know based upon our stoichiometry, it's a 4-to-1 reaction. We can calculate approximately how much this. It's also 1-to-1 here. We can say that at equilibrium, there's going to be just some of this left, but here's how much based upon our ice table we're going to have once we've reached equilibrium. If our formation expression is this, we know that is 7.8 times 10 to the 8th. We can plug in our values that we have available to us here, and then solve for our x. Solve for x, which is our molarity of our zinc hydrate that actually would go into, that would remain in solution after this reaction has progressed. Cool. From here, you should be able to tackle most any problem that I start to ask you about KSP, formation constant, and dissociation product constant. Feel free to go back and reference this as you're working the problems. All answer keys have been posted or are available to you as you're working through these calculations. Again, be reminded that you can be shooting me emails as you're working should you get stuck. I'm going to be checking those periodically to make sure that you guys are getting the support that you need. Best of luck, and fear not, I will be back soon.